negative sign.
Which negative sign?
We originally had sine 5x 1 minus sine squared x.
Oh, so I basically, so what I did was I actually switched it back. So when we look at that, we lost all the actual things. So I got rid of that. Said that's not going to work. So we have to go back and do it a different way.
Okay.
So you haven't lost anything yet. So I'm going to take this, and this is going to become 1 minus cosine squared x squared sine x dx. Okay. So now I have my 1 sine x still there, which I'm going to need for my u substitution. And I have all of my, the rest of the stuff in cosines. So what we're going to do is we're going to say u equals cosine of x. And that means du is negative sine of x, which I will change to negative du is sine x dx.
Hey, Professor, why not pick sine of x as u again?
So if I do the sine, so the problem is if I make sine or the u or sine x u, I'm still going to have an extra cosine left. Because I have cosine squared x. So one of those cosines is going to be taken up in the du option because I have cosine x dx, which will be du, but I still have a cosine left. That's why you want to work with the one that has the odd exponent, because that's going to allow you to change everything over using the Pythagorean identity and still have that one piece left over that's going to disappear when I do the du.
Okay, thank you.
All right, so I've got my cosine squared x and then 1 minus cosine squared x squared and my sine x dx. And I've got my u cosine x, and my negative du is sine x dx. So we're going to now plug these, we're going to now do my u substitution. So wherever I see a cosine x, I'm putting a u. So I have u squared, 1 minus u squared squared. And then this whole piece at the end right here becomes negative du. That's u substitution. Okay. Does that u substitution step make sense? All right. So now that I've got the u substitution in there, I'm going to go through and actually do my integration. So I'm going to pull out the negative sign. We're going to through and do this calculation all out, and I end up getting u squared minus 2u to the 4th plus u to the 6th du. So you FOIL out the 1 minus u squared, and then you multiply everything by u squared. So now we can do my integration. So I have u to the 3rd over 3 minus 2u to the 5th over 5 plus u to the 7 over 7 plus c.
Why is it u to the 6, Professor, and not u to the 4?
Well, so there's two steps here. So I'm just going to write it over here and I'll do it out. So I have the 1 minus u squared. This becomes 1 minus 2u squared plus u to the 4th when you FOIL it out. And then you're multiplying everything by u squared. So that's where the minus 2u to the 4th plus u to the 6th comes in. Because remember, that right there is 1 minus u squared times 1 minus u squared.
Thank you.
No problem. All right, now that we've got it integrated out, we have it in terms of u. I need it in terms of x, so I have to switch back to my cosines. So my final answer is negative 1/3 cosine to the 3x plus 2/5 cosine to the 5x plus 1/7 cosine to the 7x. And then my plus c is off the screen. So there's a plus c there.
And that's our final answer.
And that's your final answer. So it's all in terms of x. So anytime you do u substitution, you have to switch back to the original problem. Unless it's a definite integral, and then you can actually do the solving that way. All right. Any questions with that? Does that make sense? I know there's a lot in there. We're going to do a few more of these problems and stuff too. I know there's definitely a lot in there though. Do one more of those before I do that other one. Just looking for another problem like that. I'm going to give you guys a little more practice and things with those. Let's do that one. Let's look at this one. I have sine squared x cosine to the 3rd x dx. So in this one, if we look at it, I've got, which one's the odd one in this case?
Cosine?
Which one's the odd one?
The cosine.
Oh, sorry. I thought you said what the cosine. Yeah. So I'm going to pull out one of those cosines. So I'm going to pull out the cosine and I'm going to switch the other. So I've got sine squared x, cosine squared x, and then I've got the extra cosine over here. All right. So now I want to change this cosine squared x into sines. So I have sine squared x. This is going to be 1 minus sine squared x. And keep the cosine x.
At this point, Professor, would you be looking to make u sine of x so that du is cosine?
Yes, you want that to be your du. So we're going to make u sine because then du becomes the cosine x dx. So you're basically, whenever you pull that piece out, your u is going to be the opposite one. So in the last problem, we pulled out a sine, we made our u cosine. This one, we pulled out a cosine, we made our u sine. Because our du has got to be the one that we're pulling out to get rid of that part. So this becomes u squared times 1 minus u squared. And that piece just becomes du. Okay. And now we can do our multiplication and our integration. So my integral is u to the third over 3 minus u to the 5 over 5. See? And then we're going to change back to my sine of x. So 1/3 sine to the third x minus 1/5.
Professor, did you FOIL that out correctly before integrating?
Hold on 1 second. Eli, good. That's okay. Sorry, all I could hear was my dog barking. What was your question now?
Did we FOIL? Oh, I guess okay. Oh yeah, I guess that we didn't have to FOIL out anything because it's not.
Yeah, this one we didn't have the squared outside. So yeah, we didn't have to FOIL this one. All right, so yeah, that down there, that would be my final answer on this one. All right, so when you have, the functions all in terms of sines and cosines, you pull out the one extra one that you have, and then we can change the other one over and we can use u substitution. So this is an extension of the integration by parts that we did with the product rule. So this is a product of two trig functions, and this is how you have to actually do the integration for it. All right, so we've talked about when one of them is odd. What happens if neither one of them is odd? Then we have a situation where I can't pull one out to do it, and that's possible. That actually can happen. So let's look at a situation that happens. So I can't, if I took this one and I switched it over to 1 minus cosine squared x, it doesn't help me. I'm in the exact same situation I am in now, except I'd have cosine squared x instead of sine squared x. So and I have nothing to be able to pull out to be able to do a u substitution the way that it's set up right now. So the next thing we want to look at is there's a couple other rules that we can use. They're the half angle formulas. So we've got, so I got sine squared x is 1/2 1 minus cosine 2x. And you got cosine squared x is 1/2 1 plus cosine 2x. And the other possible one that we can use is sine x cosine x is 1/2 sine 2x. So these three rules we can use to start doing some of those other calculations when things don't necessarily work out the way we want. Because even in the last one, they're both odd. However, I could make sine x equal to it and solve it out that way. But I can't change things around in that last one because I don't have the sine squareds. So those three identities are ones that you'd want to be using for these. So let's do this one. Give you a minute to finish writing those down. And I think I'm going to make a slight modification to my lesson. I'm probably only going to do 7.2 tonight. I'm probably not going to do 7.3. So
We're using the first one, 1/2.
yep. So I'm going to use that one for this one. So and the nice thing about doing the switching it to this one is when I do my piece, I have the 1/2, 1 minus cosine 2x dx. So I no longer have the squared. So I can do some basic u substitution to get rid of, to work with this. So the first thing I can do is I can pull out that 1/2. So it's not there. So I just have the 1 minus cosine 2x dx. So now basically what I'm going to do is that 2x inside is going to cause me a little bit of trouble because I have a function inside of a function. And that's what in integration, that's what u substitution helps me with. So I'm going to make my u 2x. So that means du is 2 dx. Correct?
Mhm.
All right. And that changes to 1/2 du equals dx. This thing right here, or this whole thing, you're going to see a lot. And a lot of times they're not even going to show you that step. It ends up being known as what's called implied u substitution. So you're just going to do it and have to realize where that extra half and stuff comes from, or the third, or whatever the number is. So basically, whatever number is in front of the x is going to go outside as a fraction in front of it. So till you get the concept down of being able to just do it and see it, I would write it out and get into the habit of seeing it, especially if you're not very good with substitution. I would write that out so you can actually don't mess it up. So I have the 1/2. And I actually have a second 1/2 now. So I have the second 1/2. So I also have another 1/2 out here.
How can we take out that 1/2 when it doesn't affect the 1 minus cosine 2x? Because the other one, we could have taken out the 1/2 because it affected both 1 minus cosine 2x. But in this case, oh, is it? When it's like 1/2, is it affecting the whole?
Actually, you know what? You're right. I got to split it. I missed one step. I missed one step. So it's going to come out over here. And then this will be cosine of u. Because you're right, the half's only affecting the cosine, not the one. I missed the split step. So, because remember, anything addition or subtraction, we have to split up. We don't have to keep it all together. All right, so I have 1/2. This ends up becoming just x minus 1/2. The cosine of u is, cosine goes to negative sine, right? So negative sine, and I can change back my x to 2x plus c. Oh, I don't actually need the plus c. This one's definite. So 0 to pi. That makes sense? So I did the u substitution. I did the integral of it. And now I'm going to have to actually do my evaluation step.
So this simplifies real quick, kind of a dumb question, but it's like 1/2 plus 1/4 times sine 2x, right?
Yeah, because this is a definite integral, and we're going to be able, we're plugging in numbers. I wouldn't distribute the 1/2 through yet. We can just distribute the 1/2 through at the end. So.
Oh, I see what you mean, because it makes it simpler.
Yeah, it's one less thing you have to worry about when you're doing it out. So that x is going to become pi. The pi goes in here. 2 pi, sine of 2 pi is 0. So that's gone. When I plug in, so I've got that, and then minus. So when I plug in the 0, I got that's 0, and sine of 0 is 0. So this actually ends up being just 1/2 pi. Makes sense?
Right, because sine of 2 pi and sine of 0 is both 0, right?
Yeah, so yeah, sine of 2 pi is 0 and sine of 0 is 0. So those all kind of cancel each other out.
Professor.
Yeah.
I'm looking at an identity that says that the integral of sine squared ax dx equals x over 2 minus sine 2 ax over 4a. Is that essentially what we just did, except plugging in our defined integral at the end?
Well, okay. Repeat what you said.
It says the integral of sine squared ax dx is equal to x over 2 minus sine 2 ax over 4a.
Yes, in essence, that's what we just did. So here's your thing. Remember I said at the end of the book, there's like 100, like 180 different integral rules?
That's what I'm looking at.
Right. So they give you a bunch of them. So you can try to memorize all 180 rules, which can work. Or like a lot of those rules at the end, or those identities, can be found other ways. So like this one, we basically just did it without having that other piece in there, we just found the integral of it. So, and the other thing is you have to realize what all those letters mean and make sure you have the letters in the right spots when you do the calculations. So in this case, there was no actual A's, they were all ones. So that's why it ended up working out pretty simple in this case. So you can, on some of them, but sometimes it's just easier to remember the basic identities and work your way through it.
Okay.
So that's the problem. Is like when you get bogged down in all those rules, it's a rabbit hole.
Did you find yourself trying to find proofs of these? Like, I've always wondered, like, to what extent to take my own knowledge. And for example, like, have you ever proved ln of ex as its derivative is ex?
It really depends on how much you want to do. So basically, as soon as you get through like differential equations in Calc 3, you're pretty much done with the actual calculated math. All the classes after that point are more of your proof-based class. You have linear algebra, abstract algebra, real analysis. Those classes are all basically proof-based math at that point. Real analysis, which is typically the last class you take if you're going to go for a bachelor's in mathematics, is the proofs of the beginning calculus functions. So you do the proofs of the basic differential functions, you do the proofs of the basic integration functions. So that's what that class basically does. So it really just depends on how far you want to go. I became less and less of a fan of math the more that I had to go back into proofs and stuff for the algebra parts. I didn't mind the proofs in geometry, but I was not a huge fan of the proofs in the algebra and the calculus stuff.
So is real analysis just like a hardcore discrete math class?
No, so real analysis is the proof of calculus. So it's a proof-based class. So you're like, you were just asking, it's like, is there a proof for like this function? It's like, yes, that's literally what you do in those classes, is go through and work out the proofs on how to come up with those, the integral like Stephen just mentioned.
Cool.
So it's like proving that works. So
For
I mean,
us gamers, it seems like the people that make it through those classes, those are like the level, the real hardcore OGs. You know, I'm just trying to get through this.
yes, those are your real mathematicians. Those are the ones who are gonna sit there and do all these calculations and stuff out in the backgrounds. Not everybody gets through.
At what point is it just OCD behavior? You know,
Some of it is. It's like, and that's really, so like after you take Calc 3 and differential equations and stuff, that's actually where you'll see a split. You'll have the people who really want to do like pure mathematics or teach mathematics will go the real analysis and those type of routes. And the ones who want to do stuff split off and start doing the engineering. That's when they'll start taking the engineering classes and stuff like that, because they want to be able to apply the math, not necessarily prove the math. So right after differential equations, Calc 3 is where you start to see that split. And that's why like most of your associate's degrees will end with like discrete math or differential equations or Calc 3, is because that's when you can decide really what path you want to do at that point. So it's fun. Some people enjoy it. I enjoy teaching it. I would not want to sit behind a desk doing this all day though. It's like, I got offered a job right out of college doing that. Was going to be an engineer's assistant basically checking the math. And I'm like, nope, not my cup of tea.
You had to take real analysis so you could teach calculus?
Yep, basically. Because the concept is that you want to be, when you have to explain something, like you guys are going to ask a ton of questions. And if I really truly don't really understand the end result and all that other stuff, it's really hard for me to be able to explain it to you. So that's why, like, even to teach high school, there's a whole bunch of extra classes. Like I don't teach calculus in high school. I don't teach like the high-end stuff, but you need to know that stuff to get your degree, to be able to actually get your certification to teach even in high school. So that's why they want you well above what you actually would be teaching. So you can explain things, which is why your elementary school teachers don't know how to teach math, because most of them took English. All right, now that we're totally off track, let's do another one of these. Let's do. So we have integral of cosine to the fourth t dt. All right. So let's do this one. All right, so on this one, I don't have the extra pieces to do it out. So so here's what I'm gonna do first. That 2t is driving me a little crazy with the actual function. So I'm gonna do a quick u substitution, but I'm gonna use x. I'm gonna make x 2t. So dx is 2 dt, which is 1/2 dx equals dt. So I'm going to change this problem to 1/2 cosine for x dx. This way, I don't have to worry about the 2t going through the rest of my problem. Okay, that's the nice thing about the substitution, is that you can make the problem a little simpler as long as you follow the process to do it. So if I had to carry the 2t through the rest of it, we could. It's just one extra thing that could confuse you going forward, or that you can lose a number or forget to multiply something and those type of things and make it mess it up. So now we've got just the cosine. So let's use that rule for cosine. So it's cosine squared x is, what was it, 1? This is the plus 1. 1/2, 1 plus cosine 2x. So I change this to 1/2, 1 plus cosine 2x squared.
Is there a reason why both of the half angle rules are defined in terms of cosine?
It just works out that way. Yes, I could go through and do the proof for you, but
So
it actually is very helpful though.
So since you squared all of that, why is it still 1/2?
It's not. It's going to be 1/4 in a minute.
Okay, I was just confused.
It's going to be 1/4 in a minute. I didn't. Sometimes, and I will do this. Sometimes I will skip a step and go, oh, just put it as 1/4 and not worry about it. But I'm noticing in this class that every time I do that, I get asked where it came from. So I'm slowly not doing that. Which is fine. I don't mind. It's just I got to train myself not to do skip those little steps.
No, I just figured it out. I'm just not paying attention a little bit. It's the squared covers it all.
Yeah. So yeah, it was basically the whole thing was squared. So all right. So I take the 1/2. So that 1/2 is now 1/4. So I can pull that out. So now I have 1/8 in the front. And I got to do the wonderful long FOIL process out for this one, which is fine. Cosine 2x plus cosine squared 2x dx.
I've noticed that the dx just kind of floats along the whole time. We don't really apply any math to it.
But it's just the derivative piece at the end. The only reason that you actually have to keep it there, especially when you're doing u substitution, is kind of like what we did at the beginning. I took that dt and I made it into something else. So you can't just lose it because you can actually do stuff with it. But yeah, just unless you're doing something with it, it just stays there at the end.
But it
Just
never
like the
gets,
C at the other problem. It's just like the C is on the end, it's just there.
so we never like multiply or divide it by anything. We just kind of leave it alone at the end.
Yeah, you're not doing that stuff with it. We won't actually do anything with it until section 9.3, when we start doing a little bit of the differential equations. You'll actually see where we're actually going to use those to do a few things. So
Okay.
because we use the dy over dx and stuff like that. So all right. So I am now down at that step. So I have 1/8 the integral of 1 plus 2 cosine 2x plus cosine 2x dx. Okay, so now I've still got a cosine squared in this problem, which I still can't do anything with. So I've got to do the same rule again to that one. So this is going to be 1/8, 1 plus 2 cosine 2x plus, that's 1/2, 1 plus cosine 4x. Yeah.
Cosine of 4x this time?
Yeah, because it was already 2x. So that x becomes a 2x again, so that's how I have 4x. All right, so now, let's simplify this down and clean this up. I have 3/2 plus 2 cosine 2x plus cosine, 1/2 cosine 4x dx. All right, are we good to that point? All this work to get an integral that I can do. All right, so we've got 1/8. And this becomes 3/2x plus. Now, this is where that implied u substitution really comes into play. So I've got a 2x right there. So in essence, I'm making that u 2x, and then my du, it's 1/2 du equals dx. But I'm not going to write all that out and do all that process out. I just have to know that I'm pulling out a half before I do the calculation for it. So that becomes 2, well, there was a 2 already there, times the 1/2. And then it's sine, or negative sine actually, negative sine 2x is what that becomes.
Wait, why are we doing it at this point and not later? Oh, so you're trying to do it all in one step rather than.
Yeah, so I'm basically, so in essence, yeah, you're doing the integral. So you can split this all up and do the u substitution for each one individually, but it becomes really long, and this problem's already long enough. So this is where, like I said, that's where that implied u substitution comes in. You have to look at this piece right in here and realize that I have to do a substitution to do this problem. It's just like the chain rule. I have to do it to do the problem. So whatever number is in there is basically going to come out as a fraction in front of the problem. And then the rest of the stuff, it just goes along with it. So that right there is what gave me the 1/2. And then it stays in the problem. And we're going to see it again with the cosine 4x. So in this one, u is going to be 4x, so it'll be 1/4 du. equals the dx. So I've got plus 1/2 times 1/4 times negative sine 4x. Okay, does that make sense? Or no?
Double U substitution because it's 4x.
Right, so that 4x there was where that 1 came from, and then it just stays in the problem. That's where that 1/4 came from.
So the implied U substitution is just as easy as taking the 2 or the 4 or whatever number it is out, putting it in front. Does
As
that
a
only
fraction.
work? Does that only work with even numbers, or does that work with odd numbers too?
Oh, it'll work with any number. It'll only work though if it's 4x, 3x, 2x, 5x, whatever. It has to be a single variable. It can't be 4x squared, for example.
Gotcha.
Then it wouldn't work because when you do the derivative of that, you still have an x. So it only works when you do the derivative. The only thing left is a number. Okay, so basically it works when you have any number in front of a single variable.
Even something like pi x, it would just be
Yep.
1 over pi.
Yep, it'll just be 1 over pi. Even if it was 2/3 x, it would be 3 over 2. It just flips it over.
Okay, thank you.
So yeah, any number in front of just a single x. All right, so I've got this whole big mess. Now we got to clean it up and simplify it. And remember, my x's really were t's. So I've got to still switch that as well. So I've got 3, oh, sorry, that's not right in green. So 3 over 16x, that's 1, so minus 1/8 sine 2x. And then I got 1, or negative 1/8 times 1/8, so I got minus 1/64 sine 4x.
Professor, before, so if we just, multiply out the fractions within here, so 2 times 1/2, that's nothing, right?
Right.
And then 1/2 times 1/4 there, that's 1/8.
Yep.
Right, so, and then obviously that one at the top just leaves us with, sorry, the first number there, 3 over 2. If we put in the 2t, or I guess we're not doing the 2t's yet, but
I'm going to do the 2t in a second.
okay, so where are you getting 3 over 16? Oh, I see. I'm jumping ahead because I'm doing the t at the same time. Okay, thank you. Never mind.
That's okay. All right, so now I'm going to plug in my 2t. So all my x's are now 2t's. So this becomes, because there's now 2, so this will be 3/8 t minus 1/8 sine 4t minus 1/64 sine 8t. And that's my final answer.
Sir, why'd you change it to 3 over 8 when it was 3 over 16 in the last one? Oh, right, the 2, I forgot.
Yeah, it's 3 over 16 times 2t.
Plus a constant at the end of this one, right?
Oh yeah, plus your c. Plus c. It was there all along. It was blocked by my highlight.
I'll try that on the test.
Yeah. I'll never mark it totally wrong if there's you don't put the plus c. I'll probably just put plus c next to it just to remind you. So, well, actually, you guys are doing it on the computer, so that's why I said if you think you got something wrong, just send me your work, and I'll look at your work compared to the actual answers of the test. So, I do that. All right, so let's actually formalize all these rules that we just have done a bunch of problems. So here's the actual rules for sines and cosines. So this right here is your slide that tells you all the stuff we just basically did. If cosine is odd, I'm taking out the one cosine and changing everything to sines. If sine is odd, I'm taking out one sine and changing everything to cosines. If they're both even, I then have to use the half angle identities.
And if they're both odd,
If they're both odd, you can actually pick whichever one you want to pull out.
nice.
So you can choose which one you want to do. The thing sometimes when they're both odds, you might end up having to use, actually, no, you can just pull out either one you want. Because once you pull one out, the other one's going to become, the rest of it's going to become even, which then you can use the Pythagorean identity, same thing we were doing before. If they're both the same one, like if it was sine x and cosine x, this right here actually makes your life the easiest one to do. It's just remembering that identity. All right. The reason this works for sine and cosine is because I have that Pythagorean identity. If I didn't have the Pythagorean identity, this would not work. So like I can't use cosine and tangent, for example. Like there's no Pythagorean identity that works between those two. So sine and cosine works because of the Pythagorean identity. The next one we're going to look at is tangent and secant. Tangent and secant also have a Pythagorean identity that we can use. So this one is tangent squared x equals secant squared x minus 1. So that's the Pythagorean identity for the tangents and secants, where we can switch things back and forth. The other thing you have to remember for this is what the derivative of secant is and what the derivative of tangent is. So if u is secant theta, du is secant, or actually, let me use x's. I'm using x's for everything else. Let's keep using x's. Tangent x dx. And if u, so that's the secant one. If u is tangent of x, du is secant squared x dx. So those are the two derivatives that you'd have to remember. All right, everybody got those down, or at least a picture, or you're gonna pull them later. All right, let's use it. All right, so when I'm looking at them, I still need so when I'm looking at the rules here, I need to figure out which one's going to be the most helpful. So in this case, I'm going to use, I have the tangent squared x is secant squared x minus 1. I could also do the other direction just by moving the 1 over. So secant squared x equals tangent squared x plus 1. So we have to figure out what am I going to be able to pull out and still have that squared. So if I'm going to do the first one, I have to pull out a secant and a tangent. And that's going to change both of those to odd, which means this is not going to be as helpful. If I pull out a secant squared x, I still have it in terms of even numbers, and that means that part up there is going to be helpful for me. So really, when you're looking at these, you're looking at this part right here, because that's the piece you have to pull out, and that's going to dictate what your sign, what your U's are going to be. So we want to look at what are we going to pull out of the problem, and then we can go from there. So in this case, this one right here is going to be the easier of the ones to pull out. So that's the one we're going to use. So we're going to use tangent. Oh, it's not right back there. So we're going to use tangent squared x plus 1 equals secant squared x. And then we're going to use the u equals tangent x, and the du equals secant squared x dx. So now that we know what we're going to use, let's rewrite the problem so I can use it. So I have tangent to the 6x, secant squared x, secant squared x dx. This secant squared x right there is going to become my tangent squared x plus 1. And then the last part stays. So that is going to become my du, and everything else becomes du's. So with the sines and cosines, I kind of just switched back and forth, so it was pretty easy to figure out that the secants and the tangents, their derivatives are a little more complicated, so it's a little different on how you have to pull things out. Now that we got that part, so it's the integral of u to the 8th plus u to the 6th. So I've got u to the 9th over 9 plus u to the 7th over 7 plus c, which I will change back to tangent. So I have 1/9 tangent to the 9th x plus 1/7 tangent to the 7th x plus c. Okay, any questions? Is the process starting to make a little sense? I guess is the better question. Are we seeing how we can use U substitution with the trig rules to be able to simplify down these problems and solve them out?
It just seems like you'll have to know which of the trig rules to use when you get to a problem.
Yes.
And knowing all of the trig rules seems difficult. So I'm wondering, is there like a shorthand for that, or do you just need to know which trig rules to use?
So there's really, so like if you go back like this screen, like there's a few trig rules to remember. So the Pythagorean identities are going to be used a ton.
Okay.
The sine squared plus cosine equals 1, the tangent squared x plus 1 equals secant squared x. Those two Pythagorean identities are used a lot because it allows me to switch things to something else that can be easily done. So those two rules you're probably going to want to remember. The half angle rules come up every so often. So those can be there. The other thing you have to remember though is it's the derivative, the actual derivatives. And that's where, unfortunately, it's like, that's where the calc 1 comes back in. It's like, do you actually remember the derivative rules for certain things? So like remembering that secant x, the derivative of it is secant x tangent x is kind of important for being able to do these. But there's less of those. So this is also where that note sheet of when you're going through and studying and things that you're going to pull out is going to be helpful, because you can write some of those notes down. It's like, okay, I'm going to need, I've seen, these are the two Pythagorean identities I'm going to need. This is a derivative I'm not going to need that I just can't remember. So write it down. So, because when you're going to do this in the worlds, you have a computer. You can easily search up what's the derivative of tangent x if you needed it. It's like, that's something you could easily search for. So, but when you're going through and studying the same concept, it's like, you don't want to have everything down there, because like, you don't want to have the entire internet. You want to have the things that you're going to need to focus on, because those are the things you just can't remember off the top of your head.
Okay.
All right. Let's do one more of these, and then I'll give you the rules for tangents. All right. So we got tangent to the 5th x and secant to the 7x. So if you remember when we did the last one, so this one, I said when we pull something out, I still need everything in terms of an even exponent to be able to do my Pythagorean rule for this one. So in the last one, it was even. So I was able to pull out the secant squared to make it work. And this one that we're looking at, I've got it in terms of odd numbers. So the exponents are odd. Both of them are odd. So when I'm looking at this, I need to pull something out that's going to make things even so I can use my Pythagorean identity to do it. Because if they're not even, I can't use my Pythagorean identity. So in this case, I want to use the u equals secant x, because then du is tangent x secant x dx. So by pulling one of each one of them out, I've now made them even, so I can use my Pythagorean identity to do the problem. So this problem becomes tangent to the 4th x, secant to the 6th x, tangent x, secant x, dx. And now, because I'm making u secant x, I need to change my tangent to secants. So it was tangent squared x equals secant squared x minus 1. So my tangent's going to become secant squared x minus 1 squared. That secant's going to stay. And then I have the tangent x secant x dx. Now I can change them all to my u's. So again, you got to just look at it. It's like, okay, what pieces do I need to move out so I can do this process? All right, so now I can do my integration or my foiling, and then I'll do my integration. So I end up getting u to the 10th minus 2u to the 8th plus u to the 6th. So I get u to the 11 over 11 minus 2u to the 9 over 9 plus u to the 7 over 7 So then I switch back to my secant. So I have 1/11 secant 11x minus 2/9 secant 9x plus 1/7 secant 7x plus 2. The goal of U substitution is get it to back to those basically the power rules. So it's just that simple, quick integration. All right. So here's the rules for tangent and secant. If secant's even, I can pull out one of my secants, and then the rest of them are going to become and then 1 plus tangent squared x. So it actually doesn't matter what the tangent is in that situation, because I'm turning everything into tangents at that point anyway. So even if this tangent's odd, that's fine. I really need my secant to be even at that point. If tangent is odd, I'm going to pull out one of each, the secant x and the tangent x, and everything's going to be terms of secant. So in this case, it doesn't matter what secant is. Secant can be even, secant can be odd. It doesn't make a difference, because everything's going to be in terms of secant at the end anyway. My tangent has to be even in that situation at the end after I pulled one out. So that's why it starts off at odd. I pull one out, and then I have the even one that I can do my transformations with. Secant and tangent, unlike sine and cosine, do not have just a simple integration for them. If you just have a tangent or just have a secant, that's what the integral rule is. So the secant or the integral of tangent x is the ln of secant x. And the integral of secant x is the ln of secant x plus tangent x.
Wait, the last part you said, that's just like another identity.
just-
Just needs to know.
Those are basically identities that you're going to have to remember, because there's no way to actually easily calculate that out. So it's kind of like knowing that the integral of sine is negative cosine, or the integral of cosine is sine. Like, those are really simple and easy to remember. Unfortunately, tangent and secant are not quickly and easily able to remember. So we need to have those rules written down somewhere. I think I've got one of those set up. Yeah. All right. let's do this one, and it'll be the last one we're gonna do. So I've got the integral of tangent to the third x. So looking back at my rules, which rule am I going to use for this one?
The bottom one.
Okay. So right now I have it as odd. So we're going to split it up. The problem is I can't necessarily use the bottom one because what am I missing?
You don't have any secants.
Right, I have no secants. So let's try to split it up so I can get a secant. So if I change this to tangent x and tangent squared x, dx. Now I can take that tangent squared x, and remember that's secant squared x minus 1. So the integral of tangent x times secant squared x minus 1 dx. So if I have tangent x secant squared x minus the integral of tangent x. I missed my dx's. All right. So let's look at the first one here. If I make u tangent x, du is secant squared x dx. So this part over here just becomes the integral of u du. So that ends up becoming just tangent squared x 1/2 tangent squared x. Everybody see where I got the 1/2 tangent squared x? So that was this piece. Now this part over here, I can't do except for that integral rule that I gave you a minute ago. So integral of tangent x is ln secant x. And then we do the plus thing. So that would be the final answer that I would have. What's up, Steve?
How did u du become just tangent squared x? Because du is secant squared x dx.
Okay, hold on. See, every time I skip one of those steps, somebody asks the question.
It's gonna be me, I'm sorry.
No, it's fine. It's fine. That's why I'm like, I was running out of room. I'm like, I don't have room to write it all. All right, let me actually, I'll write out the step. All right, so u is tangent x. So du is secant squared x. So this becomes just u du, which means that becomes u squared over 2, which then becomes tangent squared x over 2.
I got it.
It's okay. Like I said, every time I skip one little step, I get asked. So I really just need to write all the steps. All right, we're not doing section 7.3 tonight. I'll rework it. It's not that big of a deal. It happens sometimes. So we'll do 7.3 next class.
Can I just see the final answer to that problem again?
Oh yeah. Right there. So yeah. We'll do 7.3 on Tuesday and 7.4 on Thursday. So I'll probably just cut out 7.7, which is fine. I don't think I've ever actually gotten to 7.7. Every class I end up always getting at least one section behind and losing that section. I'll cover it later on. So the test won't change, but I'll just push 7.3 back one class. All right. So other than that, I would highly suggest practicing this weekend. My goal is to have the practice test up probably the beginning of next week for chapter 7 and chapter 6. So that'll probably be at the beginning of next week. It'll be a little heavier on chapter 7 than chapter 6. There'll be a couple problems from chapter 6, but I'll have the majority of it being from chapter 7. Just because understanding these rules are going to help us going forward through everything else. So that's why I'll focus a little more on that. So, but there won't be any major surprises or anything else in it. I'm not going to say, oh, by the way, your entire test is based on this, even though I didn't cover it. Not going to do that. So that would just be mean and not really helpful. So other than that.